Hello everyone, my name is Anand Balakrishnan and I'm presenting PerceMon, an online monitoring tool for perception systems. This is the fruits of our collaboration with Toyota Research and Arizona State University. Um, yeah, in this presentation, I will be going over the need for perception monitoring, STQL, a temporal logic that formally reasons about perception data, the monitoring tool itself, and a case study where we apply PerceMon to a very specific application, how we can, and I'll talk about how we can extend it towards various different applications. So why do we need perception systems? As you may know, autonomous cars and semi-autonomous vehicles are becoming more and more common on the road right now. They are highly dependent on visual data to reason about obstacle avoidance, to follow traffic signs, um, and this is a very important bottleneck in the system. And if you also follow the news, we know that there has been various different accidents caused by failures in the control system of the vehicle itself. And a lot of these can be traced back to failures in the perception module. For example, the most familiar example for us that sort of brought this problem to light is this accident that happened when Uber is testing its autonomous vehicles, and a camera detected this pedestrian as a pedestrian, a cyclist, and a pedestrian, and it wasn't able to quickly reason about what to do with it, and it was still trying to decide what it was before it actually crashed into it. So hopefully we can try preventing some of these by adding runtime verification and monitors that are able to add some common sense um, checking into these perception algorithms. So the question we aim to ask is, can we design logical specifications to monitor perception systems? And can we efficiently monitor these specifications at runtime? Spoiler alert, yes. So first, what do we want out of a perception logic? We must perception data is very rich, and we must be able to pick a language that is expressive enough to handle the perception data as first class members of the logic itself. This includes supporting bounding boxes, supporting labels and conferences associated with these segmentation data, and whatnot. Um, Moreover, we want to be able to spatially reason about these objects and also temporally reason about these objects and how, for example, how they move through a frame, how consistent the detections are, or something is being detected as a car, but there's a very small dot, and we don't necessarily care about it. But if it has a high confidence, it may be an issue, right? Um, so, um, spatial temporal quality logic has been proposed by our collaborators over at ASU, which does exactly this. It handles high-level topological structures um, and reasons about bounding boxes as these set operations on topologies, and we have spatial reasoning about them. For example, the area, for example, their off positions on the frame. It is by itself an extension of TQTL, which was proposed a few years back, that tries to do very similar things, but is not able to reason about the spatiotemporal aspects of the data. For example, this follows from TQTL. We're able to specify quantifiers over objects in a scene and freeze time at specific instances to measure time elapsed and whatnot. You're also able to reason about properties associated with each of these objects, like the class, the probability of the confidence probabilities, and also able to extract the bounding box information from these objects and reason about them as topological sets. Like I mentioned, we are also able to check the offsets of these objects on the frame itself and distance between objects. And note that we can actually do these across frames, because if we get the objects in a particular frame and get the set of objects in another frame, we're able to reason about what happened between two different frames. So this is a very powerful logic, and we thought to design a perception monitoring tool that does online monitoring for these. So PerceMon stands for perception monitor, is exactly this online monitoring tool. It basically computes the satisfaction value for every new frame that it receives from the perception system. And one limitation for this, and I think for a lot of online monitoring use cases, is that we need to be able to bound the amount of history needed and the amount of future needed to actually evaluate our specification. In reality, it all turns out to be history, and we need to, yeah. So PerceMon itself has been broken down into a very core library, and it has a few different front ends. This actually allows us to have a very easy API to extend this tool to various different applications without having to worry about if it's compatible or not. So the core of the tool itself is libPerceMon, which is a C++17 library that aims to be self-contained, so that it minimizes cross-platform errors. And it basically contains all the data structures required to monitor STQL specifications efficiently at runtime. So for example, it contains fixed length buffers to store these frames, and it's able to compute the satisfaction values over this fixed length buffer. Similarly, it has a quadry implementation to do a lot of the spatial reasoning in an efficient manner. For example, set operations over quadries are really efficient. It also exposes a very simple API, like I mentioned earlier, so they can build abstract syntax trees and a really nice interface, a really simple interface for like an online monitor for such expressions. Yeah, so that being the backend, the core of the tool, we thought we'd show you an example of how it can be extended towards more real world use cases, not just as a library, but as an application. And to do that, we try to interface it with ROS and CARLA. So ROS, or the robot operating system, is a middleware framework that can orchestrate these nodes concurrently in a nice manner. Each node publishes to a topic or subscribe to another already published topic. And to actually test out some real world perception algorithms, we chose YOLO, which is a really popular object detection algorithm written in C, and it's been really popular because it's this one-shot detection for to classify different objects in the scene, and it's able to do it very quickly. And this other algorithm called deep sort, which tracks, which builds on this bounding boxes output by an object detector and uses a neural network to track them along with column filters. And so we deployed these two algorithms as two separate nodes, and we deploy PerceMon as its own self-contained ROS node, and it's each of these are subscribing to each other, and PerceMon publishes a set of satisfaction values. We also interface this entire thing with CARLA, which is the autonomous car simulator, to show that it can, if you have a ROS module, it's easy to communicate with most other things. And if you don't have a ROS module, you can actually just write C++ to interface with whatever you need to. So PerceMon itself is, as a ROS node, is initialized with a set of specifications. So we, in this paper, we show two different specifications, but it can be n number, each of which are monitored in separate threads. It subscribes to the perception data coming from YOLO and deep sort, and it publishes a vector of satisfaction values, one for each of these specifications. Yeah, so we tested out this setup on CARLA, and we ran a few different simulations, particularly of pedestrians and cyclists crossing streets in a suburban environment. This was to recreate the Uber accident, and this is a problem that happens pretty often where pedestrians are not detected when they are close to the curb, when they are in low lighting scenarios, partially occluded and whatnot. And so we try to design exactly these sort of adversarial agents, which are not really adversarial. They're just positioned in a bad way, hoping to find these examples where perception systems fail. Yeah, so as you can see here, this is our simulation. On the left side, we have a front viewing camera, and the right side is just a view of the simulation itself. And notice that there's a pedestrian right there next to the bus stop. Pedestrian is initially partially occluded, and they can actually be seen when you're approaching them. It's just that the upper half of the body can be seen, or it's like slightly hidden by a lamppost and whatnot. So what happens a lot of times in these simulations, I think about 90% of the time, is that the neural network is able to detect, the YOLO neural network is able to detect the pedestrian for a frame or two, and it does it with really high confidence. But because it's partially occluded after that, it loses that detection. And it detects it again when it's too close to do anything about it. If it was a human driver, we would have, even if it's partially occluded, we would have known, we would have seen this movement, and we would have probably stopped. We'd have taken some evasive maneuvers. But that's not the case with these specific algorithms. What's interesting here is, again, that this the neural network is able to detect the pedestrians as soon as they come out, but by then the car has already accelerated too much that it can't decelerate fast enough, and it stops exactly as it hits the pedestrian, which is unfortunate. So in this paper, we actually just monitored two different specifications for some common sense scenarios that we thought the neural network should follow. And the first one is this notion of consistent detections, where if we have detected an object with really high confidence right now, it should have had relatively high confidence in the previous frame also. It shouldn't have just appeared out of nowhere, right? And this is exactly what we're doing here. So the specification is for all objects in the current frame that have high confidence, if the object is far away from the margins, then the object must have exited in the previous frame exist in the previous frame too with sufficiently high confidence. So the reason why we have this margin requirement is because we don't want objects to leave the frame because they actually went out of the field of view. We want to be able to detect some sort of bad detections or some occluded scenarios. And we preface this with sufficiently high confidence, because if it's low confidence, usually these objects are filtered out. Yeah, and it's pretty simple that we just check if the ID existed in the previous frame. And right now, we support we are showing just the previous frame, but we can actually do this for n number of frames as long as it's not infinite, right? And turns out, as I may have alluded to before, the above neural network architecture fails on this pretty consistently. It detects that pedestrian with really high confidence for like 2 frames, and then drops it for the next 2 frames, and again, really high confidence, like when it's 10 meters away. And this is too late for it to detect it, but it seems to appear not to be a gradual increase. It's like a very quick thing. And so this is inconsistent, right? It should be tracking the pedestrians across the frames if it can. The other specification that we wanted to check was this notion of smooth trajectories. The idea here is that tracking algorithms rely on detected objects being relatively close to each other to be able to track them accurately. If they are too far apart from each other, what happens is the tracking algorithm can misidentify one object as something else or mix up IDs and whatnot. And so the specification here checks if in subsequent frames, two objects having the same ID are overlapping more than a certain amount. The 30% here is a choice that we made. It can change depending upon how frequently you take sample the perception data. It can change based on various other things, based on your assumptions about the tracking module, but whatnot. So in this specific scenario, the neural network architecture did pretty good, probably because there are not too many other traffic bounding boxes very close to the pedestrian itself. Yeah. So in conclusion, I presented a tool for perception monitoring, and I hope that we can actually use these tools to monitor real world applications and be able to detect these spurious examples that may not be detected when when you're just testing in a data set, because it may be that the data set doesn't have enough examples of very specific things. For example, pedestrians that are partially occluded. It may be that the neural network itself is badly trained, but it's not giving, or the neural network is badly trained, but it's not. We don't know what the accuracy value itself is, what data set has been tested against. It's just a black box, and whatnot. So for the tool itself, we hope to have a few more interfaces that, for example, we want to be able to write script-based specifications, and the tool should just read this and design the monitor on its own. This is somewhat similar to what SMT-lib specification does. The other trajectory for this tool is to have front ends with Python and MATLAB, because those are some of the more popularly used deep learning languages. The STQL language itself that is supported by the tool, it doesn't use the spatial temporal fragment of this logical S4U, which is really what brings about the spatial temporal reasoning. And this is something that we hope to extend in the near future. Similarly, we want to be able to support not just bounding boxes, but a whole bunch of different data types, 3D bounding boxes, segmentation data, and whatnot. Yeah. Let me know if you have any questions. Thank you.